Jeg sagde bare det, du sagde. Jeg siger bare, så
Okay. Perfect. Thanks. Okay. So today we'll start with the midway evaluation, where so I usually do it in class, but I've been told by my colleagues that it works much better if I actually get out for 10, 15 minutes. You can write the key points on the board, and then we can come back and I'll tackle them a bit, but I'll also think a bit about them before discussing them more. I put some leading questions there about how you feel about your competence in the course so far, what could be improved in the teaching to help you feel more confident and learn more, and what is working well and should not be changed or should be increased. So I'll go out for 10, 15 minutes, and then I'll be back to discuss these things. So if you have key points, that would be useful to have on the whiteboard, because then I can take pictures and think about that. So there's a trace of that. Good. So yeah, I'll be back very soon. I won't stand outside of the door listening, promise. If I see smoke coming out, I'll call the... Yes. Cool.
Ja, den her videoer, eller hvad?
Yeah, I can see that.
Okay. Skal du så til selv mig den her bekendelse? What fucking will should not be changed. Og der er så et London her. Må jeg låne en billede til?
Hvad? Er du på rygter?
Jamen, jeg kom for i sidste 10 minutter for et møde med Ida, vi skulle have is og sidelæs.
Altså, så er det også.
Jamen, jeg kom lige nu. Jeg er simpelthen kommet fra
Ja.
Så jeg sådan, nej. Og så sådan, jeg skal altså ikke få lov.
Det kan da godt lide her.
Jo, det gjorde jeg også. Jeg kunne lige sådan, jeg var sådan, jeg kunne huske, fordi der sad også nogle partner langt siden. Og så var jeg sådan, altså jeg var ikke gerne bag. Så, nej.
Selvom her, så er sådan helt ny.
Ja, jeg så, ja. Jeg kunne nemlig helt nemt se hende. Jeg skulle lige sådan bevæge mig lidt mod Ida for at se. Jeg har jo skrevet, jeg skal bare sige det.
Ja, det er fint nok. Det er også. Det er så stort.
Det er bare lidt tilføjet.
Det er også, nogle gange kan man mærke det. Altså, det er også, jeg siger også til mine veninder, altså, jeg kan høre inden for de første dates. Det bliver så snakker om sådan, altså, den der spænding, eller sådan der spænding.
Ja,
den er
det er sådan.
You're being fucked around by den person. Eller, men også, at du er interesseret.
Ja, det er med det, om du reagerer på det.
Men også, hvilke de er begge interesseret. Det er sådan, det gør begge forsvar, det er sådan meget brugt over det.
Ja, det er sådan lidt anspændt, eller sådan lidt pro forma, og gjort det.
Ja.
Altså, det har nogle ting, man skal, og det skal ikke kunne sig, altså, man skal ligesom finde ud af.
Det er også derfor, det er sådan,
Hvem er sådan på det overfladiske?
det er også bare så smart, at
Nej.
så hurtigt som muligt bødes. For lige fornemmelsen.
Ja, for ellers så kan det være helt spil, altså.
Ja, der er ikke vibes, fordi folk er sjov og
Ja, jeg kan så godt forstå, måske så er det sådan, der er mange, der gerne vil verificere det her total cycle. Altså.
Ja.
Which is fair.
Ja, man føler også, at sådan, det gør sig for, med laver.
Nå, altså, aktiviteten er jeg så længe det er noget på neutralt grund.
Så er det sådan, nej, okay. Men altså...
Vi er ude på havnen om natten.
Ja, præcis. Skal vi gå en tur? Ja.
Det var bare det forstod han, det var noget dårligt her.
Det går en tur?
Ja.
Ja, men så heller ikke rigtig at kigge.
Nej, det kan jeg forstå, det er sådan...
Men jeg tror også, folk synes, det er svært, det der med at sidde over på det. Det bliver meget sådan op.
Det er meget intens. Der skal være noget at
snakke
til fat i, ja.
Ja. Det er smart at sætte kort. Jeg har lige kommer og skal spille kort, og så kan jeg, det spiller ikke kort, eller snakker. Og der kort bliver det så meget. Ja, det tror jeg.
Det er problem for mig, når jeg er så kompetitiv.
Ja, men det skal vi også lidt det, jeg kender om dig, ikke?
Ja, det er rigtigt. Det vil være meget ærligt.
Ja. Og så kan man se sådan, er det fedt? Altså, kan de gribe den energi?
Ja.
Eller sådan?
Gør det noget for dem, eller er det bare et til det?
Ja.
Altså, er der nogen, der har film med den her? Skal jeg sige?
Det er den, der ikke virker lige, synes.
Jeg kommer ikke til at fryse, når jeg skal herfra.
Nej.
Right. Did you see what they did to the library because of fire risk and stuff?
No.
What is this here? In a bit of that? No, they just removed a lot of tables and chairs and put different rows and like old tables when they're like intensive.
Oh, so those the like
Too many people. Yeah,
yeah.
I would rather burn and die than that. So like the 3 games to sit down. Now you can sit. But the rest of the building there.
Okay, situation.
Yes.
I
Yeah, some of the biggest
even
ones.
though there was no change,
Yes. You're sure joking, no?
at least for my
That's
and then
How do you get that job? But I work with you.
but it also updated.
If you can, you have to be constant getter. No, you have to be very exciting. Yes.
Yeah, to know what
One day there is a fire you're building in the city. Didn't we invent technologies that will solve this problem? What, in like one, no, 65 and 64.
because they're not paid to notice. So why should they bother?
Megaphone, they can't have a shop stop. They have a megaphone. Yes. That's, I think, how much is a fire alarm? Like, less than a megaphone. I'd say 54. I don't know. And like, Denmark is not so high tech actually. Like you can think about it, but feels like a high tech country, but then the more you think about it, it's actually really not a bad day. Yes. And doesn't go home at 4. Really? But like what Mark says about Denmark being immature, I think of the whole time. Yeah.
Generally, when I go traveling. But that is also collided by some of the places I usually go traveling to. They seem like disadvantages. Yeah, yeah. Except for toilets and bidets. We are like the dark ages here on the
Really?
yeah.
Mhm.
And public transportation payment structure systems. I remember being in Guatemala and they had just like figured out some way when you didn't need to use your bicycle to pay for the bus. You just use your regular card. Yeah, it's different on the bus. Yeah. That's a small transaction. Why don't we just do that?
Well,
You need more time? Things good. Okay. Great.
Does somebody wants to talk me through the competence question? And I know that that person is not going to express their own perspective, but everybody's, yeah, blah, blah, blah. Yes.
For myself, I feel like it's taken some time. I'm now at a point where I feel like when I look at like the code for Simon 2 that I can.
But I do not feel that I would be able to get there on my own without the course notes and the code that you provided.
Yeah.
So it's like a case of that, like maybe like rhetorically and like logically I understand, but maybe like practically, like I'm like competent.
Yeah.
Yeah.
Okay, so I think that's very common, and that's where. So next time you'll have a guest lecturer who's a former student who was in your same situation 2-3 years ago, and now is building her own model in the clinic. It's a fancy reinforcement learning, and she'll guide you through how she has done it. And then we will do Bayesian models of Bayesian cognition, and we'll restart, right? So we'll say, okay, now we sort of show how the path looks like, and we're going to start again from scratch. What's the equation? How do we build it? How do we set up the whole code? And so on and so forth. One thing that I don't know how shared these experiences, but I gather it's, kind of the same for many, if not all. what I've also considered doing, and I haven't really figured it out properly, is maybe to split the workflow more through the example so that you actually get to, before doing multi-level, you get to restart a new example and do it from scratch so you consolidate the basic things. It has pros and cons. I haven't figured it out yet. And then, the next example before we then build a model comparison, which we do today. But I think that I'll keep in mind this as we go through, and you'll also have more informed opinions at the end. Good. Are there other comments on your level of confidence? Yes.
So I don't know how general it is, and it could just be me or something about it, but there's something about the relationship, sort of maybe mathematically, but also maybe like simpler mechanically about the fire and the data and how they go together to produce stereo. That's, I feel like we talked about it in the class, but still it's a little bit of a magic input-output scenario for me.
Yeah.
Like when we see the plots when a fire is stereo,
Yes.
how seeing the transformation from one to the other, or understanding that.
Yeah.
I think it's in methods 4 also, but it is still.
No, but that's a good point. Yeah, it is a crucial aspect of this, and I should pay more attention to that. We can go through that again, not today, but after Easter. Yes, I'll make a note. Also because there we will be using Bayes as a model for cognition beyond it being a way of fitting models. And so that's a good place to add it. Yes, thanks. Yep.
I can get a bit confused when bias
Yes.
simulation-based to what extent I need to understand the machinery behind AI.
Yeah.
These kind of steps.
This is a good point. So I'll talk more about exactly the reweighting that's behind prior sense and the simulation process that's behind SPC today, because we're going to apply the same things to model comparison. And I think I'll go, so I chose to use those packages because they make your computers able to run these things. But maybe there is a point in showing the mock-up of how the code would look like. Just less computationally efficient. Yeah, good point. Remind me, I think I'll cover it today, but remind me if I don't. Yes. Good. Other points on confidence? So let's take the next point. What could be improved in the teaching materials, blah, 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 to help you both learning, but also feeling like you're on top of the materials? Yes.
During the lectures, if you can make it even more so than you do now, zoom out once in a while and say like, why we are doing this thing.
Yes.
If patients
Yeah.
that this work, because sometimes it's very, you still detailed with all the
yes
everything, and that's great, but I think I can just sometimes get a bit lost on that and forget like, okay, what am I doing right now actually? And why is this thing actually important? It might be important in a lot of like slides or in a very like later stage in the process. But I think that helps me get a better overview of these to know how to explain.
Yes.
Does that make sense?
Perfect. Yes.
Okay. Yeah, we all start with that.
Okay, great. Yeah. Okay. Yeah, I've just taking notes because and then I'll also read out what's there. You had a point? Okay. Anybody else? Yes.
I really love the course notes, but I think sometimes I get lost a bit of like zooming out, like where we are, because it's a bit of like, here's one example, here's another example in a different case, and then parameter recovery in chapter this, but also in chapter 4, and then like, okay, which.
Okay, yeah.
So maybe, I don't know if it's just the titling of them or like a contents page, but like.
I think it's also an artifact that I've been rewriting everything And so sometimes when I'm getting short in time, it gets a bit of an info dump. So you'll see in the chapter in model comparison, the last fourth is just an info dump of all the things that I want not to forget, but that are not organized in a good way yet. Yes. So it's really a work in progress. So it suffers from that not being a handbook. It's just, yes. Good. But it's also because I feel that a lot of the handbooks out there, well, there aren't that many handbooks in cognitive modeling, but those that are out there, they're sort of not pedagogical in the way I find useful for practice. So that there's the Lee and Wagenmacher's Bayesian cognitive models. It's very, hey, here is a model, figure it out. Here is a model, I show you how you code it, and then here are 3 exercises. And then there's the Lewandowski and Farrell, which is also great, but it also starts, okay, now we do a model and I explain you what likelihood is. And now we do another model and I explain you how maximum likelihood estimation works. And then it's just, too far. But yes, so I also every year I take notes on what I should change next year according to the feedback, and these are good points. So some sort of overviews maybe at the start of each chapter or something like that. Yes.
About how it is personally, I can sometimes distinguish between what is like a sort of requirement or like just a part of the workflow to do things correctly, and what is a choice, like a multiple choice.
Mm-hmm.
You know what I mean?
Yeah.
Because then when we see examples of stuff, I can be confused, like what am I supposed to transfer to new examples?
Yes.
And where should I be creative with different?
Yeah.
Does that make sense?
Absolutely. So I think that's a very good point. So for instance, if we're analyzing the biased agent, it makes a lot of sense to make posterior predictive checks where we count how many times they pick right. But if we're looking like the whatever was called, one of you had the bad loser model, right? Where when you lose 3 times, then you change strategy. And when you win 3 times, then you change strategy. In that context, it might make sense to look at sequences of how many times do you pick right in a row? How many times do you pick left in a row? And it's still a posterior predictive check, but it's different from the ones that we've seen, right? So I try to put those examples, and I'll keep on doing that as we move on to new models. I think this is also a problem in the way I've been teaching it, where the first 6 weeks are on one model. And then it's hard to sort of keep track of what is specific to this model and what generalizes to the next. Yeah, so I think that's a very good point. Yeah. Yes?
I have a thing. I'm not sure if it's a bit of a controversial opinion, but it's at least my experience that I think this has spent some time on things that were covered fairly thoroughly in the sport and decision making.
Mm-hmm.
And I feel with the whole, for example, I'm super confused about SBC and biases.
Yeah.
So moving some of that time to those new and
Mm-hmm.
complicated things would at least benefit me.
Yeah, so my experience has been that taking for granted content, too much content from decision making in particular, is a very bad choice because not everybody is solid, and also the course keeps changing. But I hear the point of there are specific areas that would require more care than it has currently been. And then it's my problem to figure out how to adjust it. I'm not sure if any of you has opinions, but I feel like I've already taken enough for granted from methods 4, at least, for instance, going from prior to posterior, and taking even more for granted would put you on a bit of more shaky ground, because it's also nice for your confidence to say, oh, that was from methods 4. I remember this now. Actually, I really know what this means, right? But I think that these restating the point that there are certain tools that I've introduced this year that have been sort of run through too quickly and you don't get a good feel for that is very well taken. Yes. Good. Other points on things that could be improved? Yes. And then there's what is working well and what should not be changed or should be, no, that's, yeah, and should not be changed or should be increased. Yes.
There's a way in which you introduce the methods in the course that I really like. For example, I was just reading the SPC thing now this morning, where you introduce it like as this thing and it solves this problem. For me, it's just way easier to, I think, understand or to begin to understand the concept or tool if I know what problem is solved.
Yep.
So please, yeah.
Okay, cool. Yes. Maybe I should check. Love the course notes. It's nice to go through the entire workflow in detail. The lectures are highly informative and it's challenging but possible to follow, which is great. And nice that we start from bottom and move fairly quickly forward. Great. Adjusting things, that's what I want to keep doing. So tell me things, and this is very useful. That was the point we discussed before, prior and data, yes. And then we have more clear overview. That's absolutely, yes. Zooming out on the general Bayesian, yes. More about interpreting model behavior from plots. Great, we'll do it today. So this is a nice. Do you want to expand a bit more on interpreting model behavior from plots? Yes.
I guess it takes me quite some time when I watch the course, right, on what to look out for first.
Yes.
Because there could be multiple things that I notice at the same time.
Yeah.
And I think just, select the piece a little bit of like some of the new books, right?
Yes.
So what are the new methods, and then we see the output and to actually slow down and realize what we're looking for. But that might be a skill issue, but yeah.
No, this is very good points, yes. And we'll see a couple of new plots today, which I made between last night and 10 minutes before coming in. So this is actually a good reminder that I should slow down and explain them properly. Nice. Good. So as you know, I'll take these points, think a bit more about that, and add if I have something on discussions. But generally, I'll try to take them in planning the next lectures and classes and course materials. And at the end of the course, we will sort of evaluate how well that process has gone. And it might be that you need to sort of poke me again and says, well, you said you would have done that. Maybe you did it for 2 lectures and then you sort of drifted out of that. Please be consistent in doing this, right? Good. I think this is very useful feedback, so thank you. Any additional last points that you want to bring up? Good. Then the plan, right? Where are we in the Bayesian workflow? So our goal, and in this first case, was kind of a bit too simulated, but the idea is we have behaviors of beings, them being cog-sci students or non-human primates who are playing the matching pennies game. And we are interested in trying to understand which kinds of cognitive mechanisms might be involved in generating their behaviors. Since we're starting, we kept it relatively simple. We worked on the bias agents, the memory agents, and reinforcement learning / win-stay-lose-shift, which is the extreme case of reinforcement learning, right? We formalized, simulated, inferred, and assessed the single agent models, but we know that there's more information in the population than there is in one agent. So last week, we introduced the multi-level or hierarchical or mixed effect way of modeling things. and how to assess it. Because that way we can get more information out of the data. Now we wrap up our hierarchical modeling module. I have a couple of slides where I just want to ask the question, was it worth it? What have we gained from this? And then we go into model comparison. Why are we going into model comparison? Well, there's many reasons, and we'll repeat them, but just to give you an anticipation, right? As you've discovered, different groups might develop different models of how the behavior is generated. Who's right? Or, to be more fair, which of the model better describe which data? It might be that if we're comparing cog-sized students with Madagascar lemurs, right? It's not exactly the same kind of cognitive processes that are working on there, right? It might be that we have theoretical clashes with reinforcement learning coming from a certain tradition. Chris Mattis runs into the room, opens the door and yells, right? Hierarchical Gaussian filter, right? This is the only possible way. And we want to know, is the hassle of implementing a hierarchical Gaussian filter and all the issues with so many parameters worth compared to a normal reinforcement learning? It could also be that we have, active inference paradigms versus passive learning paradigms, and we want to know which is better, which of these approaches is supported by data, under which conditions. We might also have situations, and we mentioned them a bit, where we have simpler and more complex versions of the same model. We have a reinforcement learning algorithm in which we learn equally from positive and negative feedback, and a version where we're actually differentiating between the two, right? Or as you'll see next week, a basic reinforcement learning model, and one that puts into the estimation not just the expected value, but also the expected effort in getting that value. Right? And we want to know, is the simpler or more complex version a better fit to the data? Right? We might also have that different participants might be applying different heuristics, right? And we want to compare how different models fare on the population and on the participants level. So this is what model comparison is. It's a series of tools, well, really one that I'll present you. There's others that I think they're bad, so I'm not going to present them, that we can use to compare how well the model is doing in capturing the essence of the data in general or of specific parts of the data. Does that make sense? You've done model comparison before, I know. It's just in cognitive modeling, we might be using it in a slightly different way. Right? Okay. Good. So first, I want to wrap up whether doing hierarchical modeling was worth it. So we've seen three approaches to structure data. One in which we ignore the structure. We assume that all the data comes from exactly the same data generating process with exactly the same parameter values, and we use all the data to estimate it. We have a no pooling. We assume that there is nothing shared across the layers of the data. For instance, we can take participants and fit the model separately, participant by participants. Maybe because we don't want to bother with hierarchical modeling. Maybe because we think that by doing hierarchical modeling, we are sort of canceling out important differences in the participants. Big debate that's been in computational psychiatry is, should we pool across controls and patients? And it's been shown that if controls and patients come from different populations, different underlying population level parameters, then pooling them all together risks underestimating the difference between the two groups, right? But since you're becoming fantastic modelers, right, there is no reason for which you can just pull within the two groups separately. The compromise between the two positions we've seen is partial pooling, which is an attempt at saying that individuals might be different from each other, but they also share something. And we put a population level parameters as brackets prior for the estimation of each of individual level parameters, with the twist that we estimate at the same time the population level parameter and the individual level parameter. So they constrain each other as we're estimating them. So what we do now is, in a simulation, as usual, we sort of look at the true values for individuals, the true values for the population, and how these three methods of estimation capture or not capture that. So let's start with the vertical bands. Those are the what is called the population level estimates. We have the true generative mean is the black line, continuous black line. The dashed red line is the complete pooling means, which is clearly underestimated, right? The yellow line is the no pooling mean, right? So we estimate all the participants separately. We do a mean post hoc across their individual level parameters, and we get another clearly underestimation of the true mean, right? And then in the blue dotted line, we see the partial pooling, which is clearly much better than the no pooling, right? And slightly better, it's slightly closer. And that's, it tells us that at the very least, it's much better than the complete pooling one. Whether it's reliably better in this case than the no pooling mean, that's up for debate. Probably not. The dots instead are the single individuals. What we have are the agents, and the estimate for each agent, I sorted them by lowest to highest just because it was easier to look at. I had so many bad iterations of these plot. And what we see in X, the black X, is the true value. What we see in the yellow circle is the no pooling estimate, and the blue circle is the partial pooling estimate. There is no individual level estimate for the complete pooling because we're not distinguishing. So what is the estimate for each agent in the complete pooling is the red line. I hope we all agree that the red line is bad. Right. When we look at the difference between the no pooling and the partial pooling, we see that what happens is that generally the estimates get pooled a bit more towards the mean. Right? What we learn from all the other participants constrain our estimate for the participant. And it's not super clear here in this specific example, but in general, the smaller the number of trials that participant went through, the more they're pooled. You can see here these two particularly small dots, they get dragged towards the mean more than these big ones. But it's not huge. And what we can see is that the further away from the mean the dots are, the more they also get pulled towards the mean compared to the ones in the middle, right? Exactly as we would expect. Because we assume that individual variations, especially when supported by few data points, should be adjusted by everything else we learned. So does it reflect better the true values? Not necessarily, right? I don't think there's a huge difference there, but it reflects the empirical data we see plus our assumption that these participants are all part of the same population. Does that make sense? In other cases, we might see more extreme effects. Questions on these plot? Good. So wrap up is multi-level modeling or hierarchical modeling is a way of modeling sources of variations in the parameter. For instance, the sensitivity to losses in the Winds-Taylor shift might vary by participant, and therefore they might shift with different propensities. It might also be at different layers, right? We might have CogSci students from different cohorts compared to chimpanzees from different zoos, right? And so we have the species, the cohorts, the individuals, the species, the zoo, the individuals, right? 3 layers of organization of the data. And this brings challenges, right? More choices, which parameters should vary. So in a reinforcement learning, will it be just the learning rate, or should we also vary the tau in the softmax, right? The model tends to have more issues in fitting, so we need to deal with reparameterization, which we have seen. And there's more parameters to recover. It's not just the population level, but it's also the variability of the population level and the single agents. And we need to be careful in making sure that we are aware of what the partial pooling is doing to our data. So we can critically assess it and decide whether we're okay with that or not. Okay, this leads us to model comparison and recovery. And I'll just introduce the topic and then we'll take the break. So what is model comparison? Sometimes we have different models of cognitive processes. Which one is better given the data that we have? This question we can ask generally, right? Is reinforcement level better, reinforcement learning better than hierarchical Gaussian filter all over the place? We can also ask it at the participant level. So is a model of reinforcement learning versus just some random movements with a bias better predict these compared to that participant, right? Some participant might just be trying to get through the experiment very quickly. Some might be trying to make an effort, and that will be reflected in the kind of cognitive mechanisms that might be at play. Sometimes, well, I said that, if we have simpler or more complex versions of the same model, we might want to see if the more complex version is worth the effort. Ideally, that wouldn't be a problem. We would fit the most complex version of the model, and the parameter values would tell us whether the simpler model is actually better, right? So for instance, is Winds-Taylor shift better than reinforcement learning? We can just fit the reinforcement learning model, and if the learning rate is 1, we get the Winds-Taylor shift, right? Hierarchical Gaussian filter, is it better than reinforcement learning? Well, if it only tells us that the lower layer, learning the mean and variability of the external world, is used in the decision process, and all the extra layers, learning how fast it changes, learning how fast it accelerates or decelerates, and so on and so forth. If the parameters that determine their influence on the decision sort of make it disappear, then we know that it's the reinforcement learning. But unfortunately, the word doesn't always work like that because these parameters can shift with each other and compensate for each other, et cetera, et cetera. So sometimes we actually want to do the model comparison. Yes. So the idea is that we ask, given the data and more than one model, which of these models seems to describe or predict the data better. And we can apply raise or Occam and say with the least parameter. Or another way of saying that is if we can assume that the models that we are putting to play are the only possible models. And one of them is true, what in statistics is called an M-closed word. We have all the possible models and the true model is included. Then, and the data are fully representative of the population of interest, what is the probability that each of the model is true? Right, and we'll learn to calculate that. But I want to sort of front load all of these issues, which are not always front loaded, but we'll discuss that. So what are model comparison approaches, right? I don't know if you've done Bayes factors in decision making, right? They're terrible. I hate them. I'm not going to teach them. Happy that somebody else did. So there is something called the internal predictive performance of the model, which is very close, we'll see, to what you probably learned as k-fold cross-validation or leave one out cross-validation, which tries to calculate for each data point in your data or each cluster of data point in your data, if the model hadn't seen them when training, how well would the model predict them? We'll see this thing called LU and ELPD. Another approach, which I like, but we're not going to cover this here, is the mixture models approach, which basically puts all the models in the same stand script and then assigns to them directly a parameter, which is the probability that this model is generating the data, and estimates at the same time all the models and the probabilities. I put a earlier lecture that I gave on mixture models. It ends up taking probably 2 or 3 weeks to cover them properly with the full Bayesian workflow I use now because they have a lot of issues in fitting. So we'll skip that this year. But you can always look at that. And what we do, no matter the approach that you choose, and in our case, using the internal predictive performance, is that we start by doing simulation-based validation. That is, we always want to start with a word in which we know that these are the only possible models. We know which model has generated which data. We run the model comparison procedure, and then we can see how good we are at recovering the true model. Once we've done that, we can actually go out and apply these to real data. But it's kind of pointless if we don't know it works in advance. And as we'll see, how well the model comparison approach works might depend on a series of other things that we should know in advance, often even before we design the experiment. If we have observational data, as I like to work with, then you're fucked. But you need to know in how many ways you're fucked and how bad. So, yes. Let me see. So we'll start after a 10 minutes break in a very stepwise manner. Okay, we're starting. Right, so we've seen why we might want to do model comparison. And now we're going to take it one step at a time. And I'm going to get all the stuff away. So what we have from previous lectures is we already have a measure of fit in the model. Does anybody remember what that is? So this is what we get out of the infamous, yes? No, because that tells us how well the chains match to each other. They might be equally very poor at describing the data, but still all in the same region, right? Yes.
I don't know what stands out, but it's above black.
Yes. So when we do target plus equal, we're summing up different components that at the end give us what is called a value called underscore LP, log posterior probability, log posterior likelihood. It's more or less the same. And I'm recording this. I shouldn't say that, but you get the idea. It's given all these data and given the way that the model is, and given, yes, the priors, right? How likely it is that the model, after having seen all the data, would generate the same data that we have trained it on. Why is that? It's because once we train a model, when we fit a model, what we do is we are fitting a generative process. And we are sort of constraining the possible parameter values on specific distributions. So once it's fitted, it can generate predictions. It can generate what it expects the data to be. That's exactly what we've been doing in running the posterior predictive checks, right? Which kind of data does it expect after having seen the data? Does that make sense? Yes.
So I'm really confused about this thing. Is the probability of generating all the data points like this?
Yes. So let's simplify it slightly and say we have a certain distribution of data. Right, something like that. And we have a model. What we can do from the model is generate 1,000 data sets. And then we can see roughly how many times of these 1,000 data sets we got these. We got the actual data. Right? That's the it's a bit more complex than that. We want to edge it a bit so that, you know, if there's a data point here that never gets generated because it's a big outlier, we don't put all the simulations, all the probabilities at 0, right? But really it's, we have a model, we give it whatever predictor the model needs, let's say the opponent's choice and the feedback, right? We generate 1,000, 10,000, 1,000,000 simulations. How many of these are close enough to the true data that we counted as a win? Right? And that can give us a probability. Right? So the log posterior probability, the LP, is really proportional to this. But it's on a log scale because we know the probabilities are a mess. Yeah. Does that make a bit more sense? We'll get there. It's in the slides. Yes. What, sorry? Yes, awesome. So you get a LP, a log posterior probability for each posterior sample, but one across the whole data set. Not for every data point, because we're summing up. So let's say that in the reinforcement learning, you have a loop that goes through all the trials. There's a target plus equal inside. which means that at every round of the loop, it gets summed up. Does that make sense? Good. So this is LP, the log posterior probability, determined for each sample by target plus. So it keeps into account both the prior and the likelihood. LP, as has been pointed out, might have some issues. It aggregates across all the observations. Right? So we get one value for all the data points together, but different data points might be fitted differently by the model. Right? This model might be perfect for participant A, B, and Z, but terrible for all the other participants. Right? We might want to see that, because model comparison doesn't need to be a yes or no. It can be a critical process through which we assess which data are better described by which model. The second key issue, now that you're doing data science, is that it's training performance, right? So if we translate from the machine learning world, right, we are basically double dipping. We are first showing the model all the data, and then we're assessing whether it's doing well on the very same data. What's the risk in that? Overfitting, right? It might have learned the noise and not just the signal. So what do we need? We need a measure that works at the observation level. And I'll try to get this thingy away. I don't know how it's. And we've already been, yes, putting it in our stand code called log-like, right? Where we basically take what was going on the target plus equal in the model. And then in the generated quantities, we repeat the same code, but we save it. We'll see that in the context of the actual models. But not only, right? We get these at the observation level. We start seeing differential fit to differential data points. But we might also want to have something that is a test performance, right? We want to see how well the model does outside of the data that it has seen. How well does it generalize? Why is that? Because that's the best measure of overfitting. If it does really well on the training data, but very poorly on new observations, we clearly have overfitted. Right? Does that make sense? Good. So, yes, this is, let's get from the log posterior probability to something that gets us to test performance, right? So given a fitted model, prior plus likelihood plus data, we have expectations about how the data look like. So each data point can be more or less probable given the model, right? The probability of observation I given the model and the data it has observed. We then use the log of that because it solves numerical issues with probabilities. And also, if we have the log of a probability, the numerical issues with probabilities are that as we multiply probabilities, they're all below 1. So they end up getting smaller and smaller. And your computer, being a discrete machine, has only a finite number of decimals. So if you do enough multiplications, then you run against the boundary of what can be represented on your computer. Log doesn't have that issue. The second is that it becomes more intuitive. So minus log of the probability of a new observation given the model and the data is the equivalent of Shannon notion of information or the notion of surprise. So if you have a very low probability of the new observation given the model plus the data, you have a very surprising new observation. Right? If you have a very high probability, you have a very unsurprising new observation. Does that make sense? Did you have a point? Yeah. Right. This can be applied to training performance. We can look at the data that we already have, and that's what log-like, the function, was doing. We can apply it to new observations. And when we apply it to new observation, then it becomes the expected log predictive density, or ELPD. So ideally, we want the model in the model comparison that maximizes the log score of all possible future observations, right? That minimizes the surprisal in meeting new observations. That's very Fristonian, right? So the ELPD is the average log score over all possible future observations, weighted by how likely those observations are under the true data generating distributions. Right, so if you know reality, you figure it out, you know the mechanism that generates the data, right? You can calculate the log score of your model on all the possible new observations, and then you weight it according to how probable they are given the data generating mechanism. Yes.
Just to remember what was the why without the subscript that the M is in model?
M, the model, Y without the thingy on top is just all the data that you've seen. Right? And so here we use an integral because the basic idea is that if you have the true distribution, the true data generating mechanism, you actually don't need to run a million simulations. You can just analytically calculate the probability of all possible outcomes. When I look at this stuff, and it's full of that in statistical papers, this is my reaction. So all possible future observations, the true data generating mechanisms, right? If we could do that stuff, we wouldn't be doing science. Does that make sense? Right. We don't know the truth. We cannot look at all the possible future observations. So we need to find something that can approximate under certain condition that kind of thinking. So in machine learning, again, we have a procedure called cross-validation, which is born from a similar concern. So the idea is that, especially when you have a relatively small number of data points, you cannot very easily separate a training set and a testing set, which are big enough for the training purpose, but also to assess the test performance. Let's say that you're working with 50 autistic kids and 50 neurotypical kids. You want to do some machine learning on that, and you set aside 10% of the data. You take, in the best possible cases, people don't always do that, but 5 autistic kids, 5 neurotypical kids. You train your model on the 45 and 45, and then you test it on the remaining 5 and 5, right? The problem is that, especially in clinical conditions like autism, how likely it is that those 5 kids represent the full possible variability of the population at stake, or actually even of your data set, let alone of the population at stake. So what we do is often we do cross-validation. We cut the data set in K slices. And in turn, we take one slice, we train the model on all the other slices, test it on that slice. then repeat the process with the next slice. So in a sense, we eat the cake and have it at the same time. In Italian, you would say you would have both your wife drunk and the wine barrel filled. And so you have both of those, right? Sorry for the sexism implicit. It was just a fun idiom that, or your husband, right? And the beer. So we're more in Denmark. Yes. The idea is that according to the machine learning discussion, at least up to a few years ago, now it's getting a bit better. The more slices, the more folds you have, the better, right? Because you have more data to train, but also you can look at each single element separately. However, again, when we are working with, for instance, clinical populations like autism, we are making a big assumption, right? So what we want is a test fold which is as distant from the training fold as new observations would be from our samples, right? So the idea is that as we go and collect data, we probably put some implicit constraints, kid whose parents are willing to bring them to the experimental setup, who probably are better functioning unless we made a special effort, because if your kid is not very well functioning, you might not have the extra energy to do these sort of things, blah, blah, blah. And so those kids in our sample will be on average closer to each other than an external kid would be, the average autistic kid in the population, if it makes sense, right? So what we want to do is we don't want to make too many slices, because that way we can capture a bit more distance between the training and the test. So it's not that the more folds, the more accurate the prediction. It's also that the more folds, the more dependent on how well the validation set represents the heterogeneity of the population compared to the training set. So the pros are all data to train, all data to validate. The cons are it's slow. It gives you more uncertain predictions, right? And it brings worries about whether the sample is representative of new data. And then I just wanted to put 2 papers that you can go and look where we actually tested this in practice, where we did cross-validation the traditional way, and then we went and checked slightly different data. In the first case, we looked at the very same kids, but instead of retelling a story from a video, they had to retell a story from an image. And the model went almost back to chance performance, just because there are some concerns there. Okay, so what we want to do is we want to do something like cross-validation, but for our Bayesian model. So the ELPD, leave one out, is the sum of the log of the probability of observation I given the model and a training data set that excludes the observation I. Does that make sense? It's the same thing as cross-validation. You take out one observation or one cluster of observations. You calculate the probability of those observations after having refitted the model only to the rest of the data. Which implies that we should refit the model once per observation or once per cluster. What's the problem with that? Yeah.
It might take a while.
Yes, exactly. As we get into more and more complex models, it might not be ideal. I had a model that took 6 weeks to run. That was before uCloud. I couldn't even run it on 1 million machines. Okay, so what we try to do is, can we actually approximate those values without having to refit the model? And so there are some tools that we've seen before when discussing prior sense, spoiler, that can allow us to do that. So the idea is that not all observations are equal. Some observations are easy to predict from the model. Some training data is more easy to predict from the fitted model than others, right? So they are not shaping the model too much. There are many others like those. And they are less interesting to predict, right? If there are biases in our sampling process, in the way we constructed the experiment, in the way we constructed the data collection, in the data that somebody else has given us, right? We want to focus on the observations that are harder to predict, because they're likely to be more representative of the performance we will have when we go out there in the world. Does that make sense? Good. I know this is not easy stuff. So, yes.
Is it a bit related to what we talked about in the last lecture about some observations being more informative than others?
Yes, influential data points. Yes, they're also called. So what we can do is we can use reweighting, what we had seen in prior sense. Right? So the idea is that the observations that the model fits well, that they have a high likelihood, they get down weighted when computing what the model would have predicted without them. They're not very informative. The model is good at predicting them, not very impressed. I'm not giving you a lot of points for that. But those that are harder to predict, I'm going to upweight them. And I'm going to consider that your failure in predicting them is more representative of actual testing performance than how good you are at predicting the other ones. Does that make sense? So we already have a measure of how good these observations are for predicting test performance, which is given by the log-like, which we've calculated just before, right? The higher the log-like, the lower the surprise. And therefore, the less we want it to impact our estimation of leave one out ELPD. Does that make sense? So in a sense, this, however, brings us a further paradox. I'm sorry, I know this is high level and it's complicated, so bear with me and ask questions. The idea is, if we have an observation that has many other observations like it, we have a very good idea of how well the model would estimate it, even if it hadn't seen it, right? Because there's a million, I used to joke that there's a million Lasse Hansen, right? We used to have one Lasse Hansen in every year, the first 4 years of CogSci. And there's a million Lasse Hansen. So if we remove one of those, well, actually, even if we don't remove that person from the model and we look at how well it predicts that, well, it's probably going to be a very good approximation of how well it will predict the next Lasse Hansen, right? Because there are so many already there. But if a data point is very surprising, right, it probably impacted the data fitting, the model fitting quite a lot because it was very informative, right? So we're going to have a harder time estimating how well the model would have predicted it if it hadn't seen it. Does it make sense? It's a bit subtle. The idea is if you have a data point that surprises the model a lot, in the model fitting, that probably has influenced the trajectory, right? Because it has impacted the log posterior probability. And therefore, we have a worse idea of how well the model would predict a point like that if we had extracted it from the training data. So what we do is we look at the log likelihood of the different data points. We put it, right? We say, okay, how many are there with a log likelihood of these of very close to 1, right? And we get a distribution. And if we have, a normal, a data set with very homogeneous data, we're going to get something that looks like this, right? Something that looks like a normal. But if we have influential data points, we're also going to get points that are very improbable, right? And these points are going to be very tricky to assess. What by simulation has been shown that really helps is saying we are actually fitting a Pareto or a long tail distribution to these data points. And then we are going to correct the data that do not fall onto that distribution so that their importance gets smoothed. So you can see there on top the importance of the very big outlier in blue gets smoothed by the distribution, the Pareto distribution along the purple arrow. And that weight that distribution, that data point has lost, it gets redistributed here. And it's a bit hard to see, but you see that all the data points get a bit higher weight. So we are smoothing these very influential data points so that we don't make too big of an inference of a case for which we don't have very good estimates. It's still pretty important, but we don't want to overweight it because of the paradox. This is what the Lou is doing. And I put the simulation data in the handbook. But basically, this is just a process flow to remind you what happens. We fit the model to all the data. We obtain the posterior sample. We calculate the log likelihood using the posterior samples. Then we compute importance weights. So the more probable, the less important. Then we apply Pareto smoothing, which stabilizes the two influential data points. And then we use these smoothed weights to approximate LIV1 prediction. How good is the model at estimating, at predicting data after having reweighted them by how well the model predicts them? Right? Sounds a bit circular. It is an approximation. And on top of that, which will become interesting later, we get that the more the data points deviate from the Pareto fit, the long tail distribution, the more they get smoothed, the higher the Pareto K diagnostic, the higher the difference, well, let's say, the more they get smoothed, and therefore the more skeptical we should be. So we should know that the model is having a hard time, really hard time predicting these data points, and we should mark them so we can go and check them. And we'll see an example. So at this point, what we have is for each data point, we have a leave one out estimated expected log posterior probability, and then there's the density, which can tell us, as we fitted the model, are there regions of the data which are badly fitted? Right. Second, we have the sum of all these values, and we can use it to compare models. Which of the n models that we're comparing has the lowest expected log posterior density estimated in terms of leave one out? These, since that value is calculated for each sample, right, means we have a distribution. We can also see how uncertain we are in how different the models are. Finally, what we can actually do as well is, given that we have these values by observation, we can say, what if we combine different models, the prediction from different models? Do we get better estimates? Do we get better predictions of the data? It's what in machine learning is called ensemble machine learning, right? Or mixture of experts. Are you covering those in data science? Maybe not. Yeah. But you have diverse models which are able to capture diverse properties of the data. If you combine their predictions, in some cases, you get better results. DeepSeek, the Chinese language model, is really big on this mixture of experts, right? There's a lot of work both in language models and machine learning about how to combine predictions from diverse models. Good. We'll go through that again by looking at the code and how it works, right? So the setup, we simulate the data, we know the truth, right? And of course, since we want to do something interesting, we simulate half the data from model 1, half the data from model 2, right? We use a population of bias agent for model 1, in which the opponent doesn't matter, right? We simulate the second model from a population of memory agents. And as we discussed 2 times ago, I think, we're going to use a reversal learning opponent, right? And a bias agent who midway through the experiment shifts, because that means we can actually fit the model properly, right? Yes.
It's just a question, how this smoothing thing, what we gained in terms of the out of sample prediction problem. But maybe it's because I'm understanding it wrong, but I think now that it brings the model closer to the less surprising values.
Yes.
Moving out. And then I'm confused about how that then applies to, can we then estimate how poorly it will perform out of sample based on that?
So the idea is that so you can see that data point was very different from the other, right? So it would really sway your assessment of the test performance. And given the model has not been dealing with it very well, that influence is very uncertain as well. It's very extreme, but also very uncertain.
So that's the measure of how poorly it would perform if there was a whole data set of values.
Exactly. But since it's only one, we are sort of saying, okay, well, maybe we should dampen its influence on our estimation. Right? It's trying to find a compromise between taking the unpredictability of the data points very seriously and upweighting, but not being swayed by only a few. If you add a lot of those, then the Pareto distribution would have a longer tail, right? And they would deviate from the tail less. When it's only 1 or 2 or 3, then you don't want that to sway your complete estimation of expected predictions on a data set of, let's say, 10,000 data points. Yes.
Information theoretical argument.
Yes.
Optimal in that sense.
Yes.
I'm guessing there are applications where it can really matter.
Yes. But so
You want to really matter that if a model fails spectacularly on one example.
Yeah.
That's pretty problem.
and that's what I'm advocating is the tools that are standard in the field are doing that. We should know what they're doing. We should also remark that when they're doing that, they're telling us, watch out.
So that's the key.
Yes. And therefore, we can both eat the cake, use that tool, but also have it and go back and check those data points and do a critical assessment of whether we need to change our model, for instance. Yes. Okay. So we do the setup. We have two true models, bias agent, memory agents. And we generate data from those. And then on both data sets, we fit each of the models. Right? So we have a bias data set, bias agent data sets. We fit a hierarchical biased model on that. We fit a hierarchical memory agent model on that. We have the memory agents data, and we fit separately each of the two models. Does that make sense? Yeah. So we ask, will the memory model be better than the bias model on the memory agent data? That's what we want to see, right? We want to be able to discriminate the true data generating process. And we ask, will the bias model be better than the memory model on the bias agent data? Right. Will we be able to recover the true data generating process? And also, as we do so, we try to learn as much as we can about the models by looking at the different steps in the process. We look at the simulated data, right? We see on the left the bias agents, what's their cumulative probability of picking right, the population level, model is playing, if I remember correctly, with a rate of 0.8. And then each agent is sort of deviating a bit from that. And this is the memory agent. I put a black line when their opponent shifts bias. It doesn't make a difference for the bias agents because they don't take the opponent's behavior into account. But you can see that it starts curving down the trajectory of the memory agents, right? Because they take their opponent into account. Then we make sure that we save the observation-based log posterior likelihood. We check that the models have fitted the data nicely. Here I just made a very rough overview of how many divergences, the biggest R hat, the minimum effect sample size. And they're fitting nicely, because if the models are not fitting nicely, then we should be very careful, because we're not really comparing the same things. We're comparing a model that fits nicely with a model that could be done better. Then we compute the Pareto smooth importance sampling, leave one out ELPD, which is as easy to take the name of the fitted model, $ methods, Lou, and please save these warning messages. We talked about that. And then we get some warnings. And here I was trying to showcase some ways in which we can visualize them. So for instance, what I did is I took all the agents and I counted how many warnings each of them was giving me. And the code is in the course notes. And I can see that there's agent 1, 7, 14, 15, etc. that are giving us issues. However, in that specific case, I didn't plot, for instance, their underlying parameter values, so it's not really helping us much. But it's telling us that only some agents have data points that are not well fitted. Then what I did is I plotted the warnings as a function of the trial. And we can see that only early data points in the trial sequence have warnings, right? What is going on? It's very hard to understand what a model is doing only from the early trials. That makes sense, right? Is it, let's say in a memory model, right? Is it a bias that is pushing us in that direction, or is it the memory? We only have a few trials, it's hard to discriminate. And then I was saying, given the opponent running choice rate, which early on can be very extreme, the first few trials, the opponent might have played left, 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 right? Do we see difficulty in the warnings? And indeed, we see that the high-level warnings, they are all at the extreme. In the first few trials, we're quite likely to get a sequence of the same choices. So it's telling us already what the model is having trouble with. Then what I can do is I can look at the difference between the two models on the bias data set and on the memory data set. So we can see that on the bias data sets, the blue one, the true model, the bias model, is doing better, but not excessively so. Right? They're very close to each other. Why? Because a memory model can approximate a bias model. For instance, by putting memory at 0 and bias at the same level as the bias model. And that the early trials are harder to estimate. Right? You get a broader spread in both directions. Once we look at the memory data, things get more interesting. So we see that the advantage is more clear. There are more complex data. It's easier to sort of discriminate the two models, but something is happening here. All right, what is happening is that the reversal is bringing the choices of the opponent on that segment closer to 0.5. And then that makes very difficult for the two models to make separate predictions. So it's telling us that there is a specific region of the space in the middle when just after the reversal, where the two models are having a hard time separating from each other. And I'm almost done. So I'll take a couple more minutes. Then what we do is we look at those differences at an aggregated level. So with the bias data, we take the best model as a reference point, 0, and that's the bias model. And we look at how different is the second best model from that, the memory model. It's slightly worse, but there's a lot of uncertainty. And we've seen also in the Lu data just before that they were very close to each other. When we look at the complex data, the memory data, the best model is the memory model, is the reference. The bias model is quite different from it. And the uncertainty is such that we don't have too many qualms about saying that it is better. Right? The uncertainty is much smaller than the difference. We can then do the stacking weights. So if we combine them, which model's prediction we should take more seriously. And we see that to predict the bias data set, we should give a weight of 0.96 to the bias model and 3.8 to the memory model. So actually, that is giving us a much clearer picture than the other one. And in the data set for memory, really, we don't learn anything from the bias model, right? It might give us, in certain cases, the same predictions, but we could just pick the best model and we'll never learn anything new from the bias model. And so we can do power/precision analysis with that. So what if we simulate data with different amounts of trials and different amount of participants? We can see how with 20 participants and 30 trials, it's kind of crappy. But as we increase, we get better. In this case, it's F1 scores. So we can play with the optimal threshold for our design. We can also play with the task design. So if we had simulated opponents that had a constant bias, it would have been very hard, no matter the amount of participants and trials, to discriminate the two models. If we use the reversal learning, we get better very quickly. And the very last thing, we've seen calibration before, right? So we don't just care about getting the right answer. We also want to know how confident we are in that answer. And so here I take the weights on the x-axis, and then I look, given that that model had a weight of 0.25 or 0.5, how many times was that model the true one? And I didn't run this because it would have taken, I think, 6,000 simulations, so I didn't have time. But if it's perfectly calibrated, we expect the blue diagonal to happen. If it's underconfident, meaning that it's giving us a lower weight than its probability of getting it right, then we get this one, the purple one. So it's have too high weights when it's the wrong one and too low when it's the right one. And then we can do the overconfidence. And with that, plus checking the course notes, plus asking me questions and wrapping it up after Easter, you know everything there is to know about model comparison, plus some new things. This is something I made up last night. Cool. So next time it's Melina Weile. I'm not going to be here because I'm giving a talk somewhere else, but I've been looking through her presentation and it looks pretty good. And it's one of you who's developing her own model and as a modification of reinforcement learning. And it's a good, walk through what are the problems and things. Yes.
So is that the same approach?
I don't think so. It's about reinforcement learning with effort estimation. And it's about actually she'll present the model on Thursday, and then on Friday, she'll give you already have it, the basic Rescorla-Wagner model, and as a challenge to add the effort-based part, which has already been introduced in the lecture from a mathematical and R perspective, but not from a STAN perspective. Yes. Cool.